We are live, everyone. So my name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And of course, there are no classrooms right now. All of you are stuck at home. So thank you so much for joining us on YouTube as we continue to highlight amazing scientists, explorers, and facilities from across the globe. Today, we are continuing our epic SciComm Storytime series. So every day at 2 p.m. Eastern, 11 a.m. Pacific, we have been featuring all stars in science communication. Everything from people flying into hurricanes to viruses going into brains and so much more. We've had guitars, stuffed animals. Today, we've got some very interestingly named rodents. But first, I want to introduce our speaker. So we are joined live in Los Angeles, sunny, beautiful Los Angeles, by Sophia Gad-Nasr. So she is a researcher at UC Irvine, and she works on dark matter, one of the most mysterious substances, effects, whatever you want to call it. We don't even know what it is. We're going to find it a little bit more in a minute in the universe, alongside being interested in dark energy, universe inflation, and so many more fantastical topics. So without further ado, thank you so much for joining us today, Sophia, and take us away.
Thank you for the introduction. Hi, everybody. So I guess one thing that I wanted to talk about is like how I got into this. So, like, I now research dark matter and all that, but like what got me to like this stuff. And when I look back into my my childhood, I always yes, I love stars and nebulae and all that, but I remember like the one time, some of you might remember this, when the first exoplanet was discovered. My mind was just blown. I was just like, wow, there might be life out there. It just opened a whole new universe to me. And so like it was kind of the unknown part, the fact that we don't know whether there's life out there or not, that I was really, really excited about. And then of course there came this stuff that there's this whole dark universe. Like there's stuff called dark matter that we can't see. Stuff called dark energy that's stretching the universe apart faster and faster with time. And and we have no idea what these things are. So it's like, we have this amazing, unfathomably large universe that we live in. And we can see all these awesome galaxies and stars and nebulae and everything. But there's so much more that we can't see. And that is, I think, what got me so fascinated with like dark matter and the dark side of the universe, is that there's so much more of it and so much that we don't understand. I love to pick apart things that we really don't understand yet. And so that's kind of what I think my whole mentality of getting into dark matter was, from childhood until now. It's just it's the unknown. I really love the unknown. So I'm going to share this cute little slide that I have. And also, if you hear something, if you hear a bit of running going on in the background, that's because my hamsters are running on the wheel. But okay, so as you can see in this slide over here, we have the normal matter is the stuff that me, yourself, and everything that you can see are made up of. Even my hamsters, despite the fact that I have named my hamsters after possible dark matter particles before. Everything that you can see is made up of normal matter, but that's like 5% of the universe's contents. 5%. A mere 5% of that slice of pie is just all the stuff that we understand. Everything else is stuff we don't. Like dark energy makes up 70%, about 70% of the universe's content. This stuff is just causing the universe to stretch apart faster and faster, and just accelerating this expansion with time. And we have no idea what it is. We don't know. Like, this is all we know, is that it is doing that. And then we have a 25% that's owed to this stuff called dark matter. And dark matter is like, it's the same. It's matter. So when you in cosmology, when you look at like the matter density, you're actually putting matter and dark matter together. It's only when you want to look at just like, say, dark matter versus matter. So they're both stuff. It's just that dark matter doesn't interact with light, and so we can't see it. But we know it's there because when we look at galaxies and we observe stars, we kind of expect the same thing that we see in our solar system. We expect that as if you move outward, from say Mercury, Venus, Earth, Mars, and go out to the outer planets, Neptune or Pluto, if you will, whatever you choose. And you find that there's a pattern in the way that the speeds of these, or the velocities of these planets, decreases with distance. So it decreases further away you are from the sun. And you expect the same sort of behavior with stars orbiting a galaxy, because let's say like the Milky Way is a disk galaxy. And so we have stars generally orbiting around a plane, kind of like the planets orbit around a plane around the sun. And so we expect the same thing to happen, but when you plot out the velocities of stars, they're actually constant. So, I mean, the velocities remain the same no matter how far out in the disk you go. And that's weird, because when you count up all the normal matter that you can see, including gas and all that stuff, there's just not enough gravity. It doesn't provide enough gravity for these speeds. And so we know that dark matter has to be there, because not only that, but also if it really, like, if it was really just the normal matter, and you know, and that's how much gravitational potential you have just from the normal matter, galaxies would have flown apart. They just would have flown apart, because you can't, there's not enough of gravitational force in there to hold all these stars together. So there has to be something out there that we can't see, which we call dark matter. And so in this slide, you see this really pretty picture, like the bullet cluster. And so the bullet cluster is basically two galaxy clusters that have passed through each other, and this is what we call like sort of a smoking gun for dark matter. Like really tells us that dark matter definitely has to exist, because, well, we assume that dark matter doesn't interact with other dark matter particles. And so when these these are those two or well, that cluster that you see those sort of blue regions, those are basically two clusters that have already collided and passed through each other. And so in galaxy clusters, there's about a factor of 10 times more gas than there is stars. And so if there was just normal matter and there was no dark matter at all, then obviously the gravitational potential should be where the pink is here. That's the gas. Okay, so the pink in there is the gas, whereas the blue is kind of, the blue region is from gravitational lensing. And so you should have the most mass where the pink stuff is, where the gas is, because gas will drag, whereas stars will just kind of, you know, go through each other. And since, you know, dark matter is assumed to not interact, it would also pass through with the stars. But the gas wouldn't, because it drags, right? And so that's why you see this sort of, those two bits dragging behind the clusters. And when you check out where all the mass is, you actually find it in the stars, in the blue regions. So there's got to be something there that you can't see that didn't really interact, and that would be dark matter. And so that's why the bullet cluster is called the smoking gun for dark matter. The really cool thing is that we don't really understand what dark matter is, and you know, we've been working on, you know, like physicists have been working on for years a particular type of dark matter, along with other kinds. But now we're trying to look at like different possibilities, like maybe there's an entire dark sector. So maybe, you know, maybe dark matter isn't just one particle. I mean, look at normal matter, look at our universe. We have so many different particles. And so like, why would dark matter have to be any less diverse, right? And so, you know, we might have several different dark matter particles. We might have dark forces that we don't even understand yet. Hence the Darth Vader little icon that I have up there. But there might just be an entire dark universe that we have no idea about. Like, so dark forces, you know, different dark matter particles, and it's so exciting to be a part of this. I work on this type of dark matter called self-interacting dark matter. So in this type of dark matter, dark matter particles do interact with each other to a certain extent. So like the bullet cluster right here would put certain constraints on how much it interacts, for example. Because in order for this to happen, in order for the dark matter to have been able to pass through, right, that obviously puts a constraint on how much interaction the dark matter particles can have with one another. I feel so fortunate to get to be able to do this and work on one of these amazing, mysteries of the universe. Then of course there's dark energy. Um, I've not worked on it yet, but it's definitely something that I'm interested in. As you can see in this little cool graphic down there, the history of the universe, kind of starting from like what inflation and moving out, where the cosmic microwave background is, and then off to today. And if you notice that when you look at the graphic towards today, it kind of bends outward. That's because the expansion of the universe begins to accelerate rather than it just being straight and just expanding. It's actually bending outwards because it's expanding faster and faster with time. And you can kind of see that in that cool graphic. And so dark energy is, again, something that I really, really would love to dig into, just because, and mind you, these two are completely different things. So often I think people get confused and wonder whether, dark matter and dark energy have any relation. And actually the answer to that is that they really don't, except for the fact that they have the name dark in them. And dark is just to say that, we don't understand what it is, we can't see it. And so that's the only thing that they have in common. But dark energy is not matter, right? So they're not the same. They're two different things, both of which we don't understand in different ways. Dark energy we understand far less, I would say. And so, I would love to get a chance to sort of dig into that and kind of try to figure out how dark matter, might evolve, or dark energy might evolve in the universe. And the cool thing is that depending on what dark matter or dark energy is, I'm sorry, what dark energy is, that tells us sort of how the universe might end. And so, we might end up in like a heat death, where basically the universe has expanded so much and things have cooled off so much that there's just no energy left to make anything else, and it just dies. I know. Very grim. And that's probably the way the universe is going to die if we have dark energy down correct. Probably don't, because we are just a snapshot in the universe's history. Like, not even a snapshot. I mean, in its 13.8 billion years, humans have been around for like what, a few million. So it's like, it's the Earth in itself has only been here. Well, the Earth in itself has been here for like 4 billion years, but humans, we've not been here long enough to see anything. And then when you look at what physics has done, and for example, it's like what, a few hundred years where we're actually working on this stuff. So we probably, I think we've been working on dark energy since, well, it was discovered by in year 2000. So like, we're 20 years in. We knew that it kind of existed before, but it was actually discovered sort of with experiments. I think it was before the WMAP satellite. And yeah, so that's what mapped sort of how the universe is actually expanding faster with time. So like, we're only 20 years in. Like, that's not a lot of time to have observed the universe and to understand, what dark energy is. But the cool thing about the universe is that, as far, because the speed of light is finite, then, if, for example, the Andromeda galaxy is what, 2 million light years away. So that means that it takes light 2 million years to get to us, because that's how light is defined, like the light speed. So when you say something is 2 million light years away, it just means that it would take light 2 million years to get us. So we're always looking at Andromeda as it looked 2 million years ago, and the further back that we look in time, we see the universe even younger. So if it's something that's 2 billion light years away, then we're looking at the universe 2 billion years ago. And so we can track how the expansion has changed, and that's what we've done. And we've come up with what we know so far, which is not all that much. And so, all in all, I think it's all the stuff in the universe that we don't understand that really gets me. Even black holes are fascinating, but like, and how they might tie into dark matter. That's the project that I'm going to be working on in a bit, which is really exciting. And so, yeah, I mean, that's really my story. As I mentioned, I've had hamsters who I named after possible dark matter particle candidates. Those were Sterlini and Axini. Today we have, I think that's a Gravitini running on the wheel right now, named after the graviton. So Sterlini was named after the sterile neutrino, which could be dark matter. If the sterile neutrino, if we were to detect it, that's definitely dark matter. Axini is named after the axion, so that would be dark matter also. Um, but Gravitini is named after the hypothetical particle that called the graviton, which would mediate the gravitational force, assuming that it was. But we also know that Einstein's general relativity tells us that gravity is actually not a force; it's just the way that mass bends space-time. So it's just the bending of space-time that mass causes. So that's okay. Gravitiny's still happy. And Gluini is the gluon, which is the mediator of the strong force. So he's I think he's sleeping in his little bed. He's always squinty-eyed and everything. That's how I tell the two apart. Now that brings me to my next slide, which is my thank you slide, which of course had to have my hamsters in there. So the two little white fellas, those are the ones that I have right now. The one in the center is Neutrini, named after the neutrino. He was special. And then the two on the right are the above is Axini and below is Sterlini. And yeah, that's all I have for you, really. Aside from showing you my hamsters, if you'd like.
That's fantastic. Well, thank you so much, Sophia. You are our only hamster-based part of our presentation, so we really appreciate that to kick off or have near the end of the day for SciComm story time.
Yeah.
So we are ready to dive in with questions. We've got a bunch of people on YouTube that are already starting to type them in. That's fantastic. Just let me know where you're joining from, and I'll share as many as possible. But I want to start with one that we get every one of our sessions. It's a good kickoff, gives us time to get some more coming in. Sophia, what is your favorite part of your job, if you can possibly pick one?
Okay, so I actually work on simulations, so it's like because I do like a bit more theory, so I don't do observation. And I think what's so exciting about that is not the coding. Okay, coding is great when it works, but otherwise it's very stressful. But the really exciting part is that I get to kind of play with toy universes, because these are universes that are simulated, and yes, they look like our universe, but it's a toy universe, so I can like go and pick anything that I want in any time and look at whatever I want. And I think that's what's super exciting about my job right now.
Fantastic. All right, we've got a question from Timberwolf in Washington on YouTube, and he wants to know, what is your favorite aspect about studying dark matter and dark energy? You sort of, I mean, we can't possibly explain all this in a 10-minute talk, but is there anything specifically that just like blows your mind?
So okay, so since I study dark matter, I'm gonna focus on that. Like I would like to study dark energy. I haven't done that yet, but so I think the most fascinating thing is that well, it's necessary to explain how the universe got here and how it still looks like what it does, because otherwise galaxies would have flown apart, because dark matter holds them together, right? And it also needed to sort of be there in the early universe when everything was super dense and hot and compact, and and there were these little sort of little wells where normal matter would try to fall in, but at that time everything was super compact, and so normal matter interacts with photons, so photons kept pushing them out, but dark matter doesn't. So dark matter was able to kind of like coalesce and form the seeds for the galaxy that we see today. So we know that, but particle physics doesn't have a dark matter particle in it. And so it's like there's definitely new physics here that we don't understand. And I think that's what fascinates me most. I know that was a long answer, but.
Hey, we love the enthusiasm. That's awesome, Sophia. All right, Emily Calandrelli is tuning in as always, and she wants to know, do you stargaze without special equipment? And if so, what do you look at?
Yes, I do. Mostly when I get out of the city, which isn't too often. Unfortunately, Los Angeles is not very great with the sky. And I'm originally from Toronto, which was also not very great with the sky. I'm doing my school in Irvine, right? So I'm at UC Irvine, which is slightly better, but also not great. But when I do look up, like, what the things that I would like, that I really love to look at when I get out of the city, is the band of the Milky Way. That, and then catching like random meteors kind of passing through, burning in the atmosphere. That's always exciting. I love that. And I think typically in the winters when we see the Orion Nebula, that's a naked eye object. So you can actually see the Orion Nebula with your naked eye, assuming you have good enough skies. That's another thing I love to look at when I look up into the night sky.
Fantastic. I encourage everyone, I mean, you mentioned Toronto and LA, not known for stargazing, but wherever you happen to be joining us from today, there's probably either a national park, a state or provincial park, or hopefully a dark sky preserve, and you can really get the Milky Way, and it's one of the most magical things you can do. We've had this in every one of our astronomy talks this month, and it's so cool to mention. All right, we got some technical questions that I actually can't just memorize, I have to read off. So David wants to know, other than finding the smoking gun for experimentally verifying dark matter, would experimentally verifying inflation excite you the most? Like, what would excite you the most as a discovery to find?
Okay, so a very short answer to that, yes. That would excite me very much, because inflation explains so many things that without, you kind of just have to assume the universe was just lucky and it just kind of ended up the way it was. But inflation explains certain things, like, we have a sort of flat geometry. Our universe is flat rather than positively or negatively curved. What does that mean? It just kind of means that if you shoot two lines, when you think, because we're thinking about this in 3D, and it's very hard to picture in 3D what flat means, So, but it's basically, if you shoot two lines parallel, they will end up parallel as far as you go. But if you lived in a positively curved universe, you shoot two lines parallel, they will cross eventually. In a negatively curved universe, they will diverge. Okay, so that's one way to think about it. If we so the gravitational waves that we're now experimentally detecting are from black holes. There are these B modes, though, which would also be gravitational waves that would have been caused by inflation. If we were to discover that, that would prove that inflation is real, and I would probably have a party at that
time. So how big a party? Like a really good party? Are we all invited to the party?
You're all invited to the party, yeah.
Fantastic.
I'm pretty sure the whole world would be partying.
Yeah. Sophia, I want to follow up with this question because we're diving into some pretty heavy science now, and I know we've got some adult audience, which is great. But for any kids watching at home, are there any books or resources that can explain this to someone in middle school or high school? Anything that really jumps out as being an excellent way we can teach people?
So with books on that, I find that a lot of popular science books are really digestible. There was this one that was called, I think, The Dark Cosmos, the Universe, the Mystery of the Universe's Missing Mass, something like this, but it's by Dan Cooper. That one, it's a bit old, so you would, it's before, it was written before, like, the Higgs boson was discovered, for example. But that one explains dark matter, and so and dark energy and and a whole bunch of other stuff. Super book. I've read that. That would be, I think, something that would be a bit easier to digest and fun. So like popular science books like that are what I would recommend.
Very cool. Some others, I know there's the 4% Universe. Lawrence Krauss is a fantastic science writer. Stephen Hawking did some fantastic stuff before he passed away. So there's resources out there. It is a complicated science. It's like quantum physics too. It's like not easy to understand, but there are some great things out there. Thanks, Sophia. All right, another complicated question. Sal in Buffalo wants to know, if the universe is expanding, is the ratio of dark matter energy to actual matter changing? Do we know this at all or not?
Okay. So yes, the ratio of dark energy, dark matter, and normal matter do change. In fact, in the if you go back far enough into the universe, at one point radiation, so like photons, light, dominated. So most of the universe was radiation at some point. The thing is that when with the expansion, you know, you have matter, so that includes dark matter as well as regular matter. You know, as the universe expands, it's like having like a marble in a cup that where you blow up the cup, but the marble stays the same, right? So there's so much more space, whereas the marble is just still that one thing because you're stretching in volume. Okay, so you're kind of stretching in three different ways, so or in three different directions. Um, and so you're basically you're becoming less you're becoming less stuff per unit volume as the universe expands. Radiation also loses energy to this thing called redshift. Okay, and so as the universe expands, it's losing an additional factor of energy, and so that's why you don't even see it on the chart anymore. Right now, like it's like I think what point point one or 0.01%, sorry, maybe no, it's more than it's like 10 to the minus 5, so that would be like 0.001%. It's just negligible. You can kind of just toss it aside now. Dark energy is constant though, so no matter how much you know, if you had just let's just call it a unit, if you have like 1 unit per per unit volume, or one let's say marble per unit volume. As the universe expands, you still have one marble per unit volume, whereas dark matter would now become like half a marble per unit volume because of the expansion of the universe, right? But dark energy is constant, which is why now it's dominant, and in the future it will actually be the most dominant component. And basically you can almost call matter and dark energy negligible. So yes.
That was great. Again, complicated stuff. We really appreciate you trying to distill it to a 1-minute answer. That's awesome. All right, I'm going to take 2 more questions. I love these questions. I love how this one ends. So Jeff wants to know, when considering the size of the universe and us, can you put these simulations that you do in perspective, or is it just too mind-blowing?
Can you repeat the question one more time?
Yeah, so how it's written is, when considering the size of the universe and us sort of in relation to that, can you put the simulations that you work with in perspective, or is it too mind-blowing to sort of comprehend the scale of all this?
So okay,
I don't know. I wish I
I'm
had
not.
more of Jeff on YouTube. If you want to give a little context and I can pass along a little more context to that, that would be great. Yeah, okay. I can give you the other question while we're waiting and see if Jeff can send us that information. So the Young family, they've been joining us all month long, which is fantastic. So we really appreciate them tuning in again. They want to know, when did you know this was the sort of thing that you wanted to do for the rest of your life? Or have you just always known since you dove in with science?
Okay, this is a really good question, because I'm not that, I'm not that person who, knew from childhood that I wanted to do, that I wanted to work on space. I was definitely fascinated by it. I loved it. I was, dark, like dark matter, dark energy, black holes, the fact that we don't understand the singularity or whatever, we can't do anything with physics there. Like these things all fascinated me, but I was more like my dad has a PhD in applied statistics, so like he's a mathematician, and so like I was more math sort of. I was more mathy at that time because my dad kind of taught me math beyond the curriculum, and I used to like ask him to make me math tests for fun. And however, my dad's Egyptian, my mom's Polish, by the way, and so but my dad's Egyptian, and if any of you who are like at least Arab or from the Middle East or something might know that you're expected to become like a medical doctor or an engineer or whatever. And my dad wanted me to become a medical doctor. I couldn't do that because I can't deal with blood. And so when I entered college, I did it as an undecided student. So I did it undecided, and I came across an astronomy club that kind of led me to where I want to be. And so basically, I would say the beauty of the universe opened up physics to me, and then physics is what kept me here. The physics of it, the beauty of the physics of it, and understanding how things work.
Fantastic. All right. Another quick note. You mentioned something earlier, the Higgs boson. So I want to mention that, like, we've had 2 major discoveries in physics in the last year. We've had the Higgs boson. We've had gravity waves. Can you explain a little bit about your knowledge of those, just for people at home that might be keen to learn a little more?
So very, very, like, I guess very simply, the Higgs boson is something that kind of is why we have mass. So why we have mass at all. Um, and it happens to, if you look at sort of like, if you look at the early universe, it happens to not interact with photon or something. And so like in this, it's a very sort of complicated mechanism, but it ends up sort of leaving the photon out, which is why the photon has no mass, whereas everything else does. So that's what the Higgs boson is. Gravitational waves are basically this sort of outburst of energy when something cataclysmic happens. The Earth also produces gravitational waves, but they're so small, right? Because the Earth is tiny.
We're nothing.
We're nothing, exactly. But everything produces gravitational waves. It's just that the cataclysmic ones are the ones that are going to produce something that we can actually detect. And the merging of two black holes or neutron stars is definitely one of those.
Very cool. All right. What I'm going to do is have Jeff, if you want to email us, and I'll pass along the email address for Exploring by the Seat of Your Pants in the chat bar. We can get that question with more context a little later, and we can say hi to a hamster too. That is adorable. Put it in the middle of the screen,
This
a little
is,
bit. There you go. This way. There you go. Hi.
Say hello.
That's
to the world.
a first in Exploring by the Seat of Your Pants history.
I'm sorry?
Sophia, that's adorable. I just said that's the first. We've never had a hamster before. So Sophia, before we wrap up, is there any last message you want to share about how people might be able to learn more about the work that you do and get excited the way that you are about all this fantastic stuff?
Yeah, sure. I mean, aside from reading like popular science books, you can follow me on Twitter. I'm astroparticle everywhere. On Twitter, on Instagram, you could find. I have a page on Facebook as well. Twitter, I'm very active on. I'm also going to be doing a YouTube series soon, so you can pay attention or keep sort of follow me on Twitter or something, so you can get the news on that, as well as my blog, which is astroparticle.com. So yeah.
Fantastic. Well, thank you so much, Sophia, for joining us today. We so appreciate you continuing to help us in our SciComm Storytime series. Again, we got the last few sessions coming, 2 p.m. Eastern, 11 a.m. Pacific. And for now, I just wish you a wonderful rest of your day enjoying sunny California.
Thank you. And thank you for having me.
All right. Bye for now. See you soon, everyone.